Scrabble's a board game where players score points by creating the best words from a limited number of letters available to them. On their rack are 7 that are pulled from a bag of 100, each with their own point value. Since the board has all kinds of double or triple value bonuses, the game has an extra layer of strategy where the longest words are not necessarily the best. It was while playing a game with my friend Sam that he posed a question which ended up being a lot more interesting than it first sounds. How many unique Scrabble racks are there? Finding the answer will be the focus of today's video, where, by the end, we'll learn a new way of counting possibilities for when objects can be chosen more than once. If you've ever learned about permutations and combinations, your first instinct might be to start at the top and work your way down. If we've got 100 tiles and 7 available spaces, then we have 100 possible tiles for the first, 99 for the second, and so on until the last tile is filled. Multiplying all these terms together gives us an upper limit for the number that we want, which we can write as 100 factorial over 100 minus 7 factorial, or 100 permute 7, and is equal to about 8 times 10 to the 13, which is pretty huge. But if we want to tackle the question of unique racks, we've clearly overcounted. Encoded in this number are the assumptions that we not only care about the order of the tiles on the rack, but also consider each of those tiles to be unique. Addressing the first is simple enough, so let's give it a go. Just as in the whole bag case, for each group of 7 tiles, 7 can take the first space, 6 the second, all the way down to the last, giving 7 factorial ways of arranging the tiles on the rack, so we have this common factor of 7 factorial that we can divide through by. This cuts our last number down to 100 factorial over 100 minus 7 factorial times 7 factorial, or 100 choose 7 possibilities, which comes to about 1.6 times 10 to the 10, a reduction by a factor of over 1,000. The second assumption, however, looks a lot less tractable. Clearly we aren't able to distinguish tiles of the same letter. The first or the sixth of the 9 A's will all look identical, so we know that we've overcounted for each letter that appears more than once. But it's not like we can just reduce the tile bag from 100 to the 27 unique letter tiles, the alphabet plus the blank tile, because we can have multiple of the same letter on a rack. It seems like balancing everything with this top-down approach is hopeless. I encourage you to pause the video and give it a go if you're unconvinced. The answer is going to be at the timestamp in the top right if you want to compare. For now though, let's leave this specific question and learn a new tool which allows for a more bottom-up approach, which will be very useful for our question. Consider for a moment a sequence of numbers which follow some pattern, like the powers of 2. We can condense such a sequence into a rule, say a sub r equals 2 to the power of r, and unless you really know your powers of 2, you can't recover information about where you are in a sequence just by looking at the terms, which could be useful. We can't just add the position of the sequence onto 2 to the power of r, nor multiply the two together, since that information would be absorbed into the number. Instead, let's try introducing a dummy variable, like x, which won't be absorbed. If we change the rule to 2 to the power of r times x to the power of r, we'll still get each term in the sequence, but the power of x will also tell us where exactly we are in the list. In fact, instead of dealing with a sequence which is essentially n different expressions, we can just add each of the terms in the sequence together to form one function. We couldn't before since adding pure numbers together would just lead to a new meaningless number, but now that each term has a unique power of x, they remain distinct. If you know your Taylor series, you might spot that this is the expansion of 1 over 1 minus 2x, making it the generating function for our sequence, since it creates each term with increasing powers of x. Though satisfying to see so compactly written, it's actually the long polynomial form which will be of the most use to us, as we can get so much information that we can read off and manipulate from just one line. Sometimes thinking of familiar functions as generating functions gives way to some new insights. Let's find out what the generating function for n choose r looks like. If a sub r equals n choose r x to the power of r, where n is a specific integer, we'll get a sequence that looks like this. If we add the terms together, stopping at r equals n, we should get something that looks pretty familiar. This is exactly the polynomial we'd get if we expanded out 1 plus x to the power of n. So why does expanding this power of 1 plus x lead to each coefficient being a choose function? To make things clearer, let's take a look at the expansion of, for example, y plus x to the power of 5. Multiplying everything out, and if we collect all the terms, we see that if we add the powers of x and y in each, we get 5. Each term has 5 power spaces that can be occupied by x and y some number of times. Let's take x cubed y squared as an example, where x takes up 3 spaces and y takes up the rest. The coefficient of this term is related to how the power spaces are filled. From 5 brackets containing an x, we see that 5 x's could occupy the first space, 4 can occupy the second, and 3 the third, so 5 factorial over 5 minus 3 factorial possibilities so far. But since all the x's are the same, we've overcounted by 3 factorial, the number of ways that we can arrange 3 items. Once the x's have been sorted out, the y's fill in the other spaces automatically and in only one possible way, so we multiply again by that one possibility. This means we'll end up with 5 choose 3 multiples of x cubed y squared, a fact which generalizes to all other coefficients. You can interpret the power filling as involving not x and y, but x 1 time and x 0 times. In fact, that's exactly how we should interpret the expansion of 1 plus x to the power of n, and the kind of thinking which will let us tackle our Scrabble problem. Say we were flipping a coin n times, and in each event there's only one way to get 0 heads and one way to get 1 heads. This is the generating function for one event. The generating function for n events would be x to the 0 plus x to the 1 all to the n. When we expand it, we get choose functions as the coefficients of each power of x, as we showed a moment ago, which correspond to the number of ways that we can get some number of heads out of n flipping events. Let's use an example to see why. Suppose we flip 3 coins. We get heads, tails, and heads. X to the 0 plus x to the 1 contains all the information about what could happen, and in each case, x to the 1, x to the 0, and x to the 1 are what did happen. This overall outcome of specifically heads, tails, and heads is captured by multiplying each of the individual outcomes together. There's only one way to flip heads on the first go, to flip tails on the second, and heads on the third, so multiplying the coefficients gives all the ways that the combination of the three can happen. Not only that, but multiplying the powers of x together will add the powers, in this case 1 plus 0 plus 1 is 2, to give x squared as the new power of x. So this outcome is part of the 2 heads in 3 flips group, and can only be done one way. There are of course other ways that we can get 2 heads in 3 flips, and the number of ways we can get this outcome would be the coefficient of x squared in the expanded expression. For example, we know there's only one way you can get 3 heads, or no heads, which is exactly what the coefficients are telling us. It's amazing that we can get all this information that we could want about any number of heads in any number of events by only expanding some brackets. And this process extends beyond the binary outcomes of a coin flip. Say we were to include an x squared term in the generating function for one event, which introduces the possibility of x being chosen twice. If we consider a bag containing 2 identical balls, from which we can pick 0, 1, or 2 in each of 5 rounds, we create a situation that sounds very similar to our Scrabble case, with an associated generating function that we can deduce to be x to the power of 0 plus x to the power of 1 plus x squared all to the power of 5. When we expand out our polynomial, we'll get powers from x to the 0 all the way to x to the 10, and if we interpret the result in exactly the same way as the coin flip case, the coefficient of x to the 10 will be the number of ways that we can end up with a total of 10 balls once all 5 rounds are concluded. Clearly there's only one way, you need to pick 2 for all 5 events. As another example, x to the 7 could be built up by multiplying powers of x in orders such as 2, 2, 2, 1, 0. Or 1, 1, 2, 1, 2. Or a number of others. The coefficient 30 is the sum of all these individual cases and tells us exactly how many ways we can have 7 balls at the end of the 5 events. Before we tackle the Scrabble problem from this new perspective, let's summarize what we've spoken about. Number 1, we can write sequences of numbers as polynomials where the coefficient of the nth power of x is the nth element of the sequence. Number 2, we took a look at the sequence a sub r equals n choose r up to the nth term, and found its generating function to be 1 plus x to the n. Number 3, we talked about why n choose r is involved when expanding 1 plus x to the n. It counts how many times we can get r number of successes out of n events, when there are only 2 options, 0 successes or 1. Number 4, we showed that if the generating function for one event has powers of x greater than 1, more than 1 success per event is possible. Now we're ready to answer the question, how many unique Scrabble racks are there? This is a list of the number of each tile in the 100 tile bag. Let's imagine that the bag was made up of 12 E's and 9 A's to start with. Since a rack has a maximum of 7 tiles, we can further reduce our bag to 7 E's and 7 A's, since you can only have a maximum of 7 A's on a rack, not 8 or beyond, so having excess A's in the bag really doesn't matter, likewise for the E's. When we represented n coin flips as a generating function, we called an event one coin flip. Here we'll call an event choosing a tile of a particular type. A can be chosen up to 7 times per event, so the generating function looks like this. The same is true for E, since the situation is symmetrical. So how many unique racks are there in this simplified version? The first event is choosing the A's, then the second event is choosing the E's. So our new generating function will be 1 plus x squared, and so on until x to the power of 7, all squared. When we multiply it out, the power of x represents the length of the rack the two events combined can make, and the coefficient of that power represents the number of unique racks of that length. We can dismiss all the terms after x to the power of 7, since we only care about up to 7 tiles in a rack, and we end up with this expression. So, for our A and E bag, we have 8 possible racks of length 7, which for such a small number is easy to count and verify. All we need to do now is apply this process to all of the other tiles. A, E, I, and O all have more than 7 tiles, so they'll have generating functions up to the 7th power. N, R, and T each show up 6 times, so they go up to 6, and so on for all of the others. Once we raise each generating function to the power of the number of letters which share it, and multiply it all together, we'll end up with this final, huge generating function. Once we expand it out, we'll have all of the information that we need. The coefficient of x to the power of r will be the number of unique racks of length r. I'll skip to the final expansion to save some time. You can just get Wolfram Alpha to do all of the grunt work for you. Our final generating function, up to the 7th power, will be this. Near the end of the game, you'll start to run out of tiles in the bag, and so your rack can have a length less than 7. What's great about this approach is that we don't have to recalculate to find the number associated with the rack shorter than 7, it's all included in the expansion. So, for the number of unique racks to include all situations, we just need to add each of these coefficients up, which gives 4,114,349 unique Scrabble racks. So, there we go. What seemed like a simple problem to begin with made us reassess how we think about counting and the shortcuts that we can use. Before I used this method, Sam had written some code to manually count all the possible racks, initially taking 2 hours to run them, and getting whittled down to less than a minute with some optimizing. When we showed each other our answers and they agreed, it was really cathartic and reminded me why problems like these are worth the hassle. They're not a particularly exciting number, the approach to finding it was really something, and hopefully the whole thing was of some use or interest to you. Thank you very much for listening.